Welcome to Void Realities. If you're awake when the world sleeps, you've found the right place. Here, the lines between dreams and reality blur, and you can drift away into a world that feels like it's just for you. No rush, no pressure. Just a space for you to unwind, let go of the noise, and find calm in the quiet of the night. Whether you're seeking peace, wonder, or something to help guide you into sleep, Void Realities is your escape. Sit back, relax, and let your mind wander to the edge of the unknown. Welcome to the void. Time dilation and the science of aging slowly. You notice how time feels longer on quiet mornings and shorter during busy afternoons. But in physics, this isn't just a feeling. Seconds can truly stretch. Here we begin to listen to the clock of the universe itself, and you discover that time, like a slow tide, changes with how you move and where you are. The morning begins softly. You open your eyes and see the pale light spilling through the curtains. The air feels still, almost holding its breath. Your mind is clear, your body unhurried, and the seconds seem to arrive with long pauses between them, as if each one has more space to unfold. You lie there, watching the way light changes across the ceiling, and for a moment it feels as though time itself has slowed to match your calm. Later in the day, the rhythm is different. Your hands are busy, your thoughts dart from one task to another, and hours seem to vanish without asking permission. The morning's stretched seconds have given way to quickened ones, slipping past in a steady stream. It feels as though time has changed its mind about how quickly it wants to pass. We often explain this as perception, the way your brain measures moments based on your attention and emotion. But the truth is more remarkable. In the physical world, time can stretch or contract in ways that have nothing to do with mood. It's not just in your head. The universe itself holds clocks that tick at different speeds. The idea sounds impossible at first. After all, you've grown up believing that a second is a second, no matter where you are or how you move. And yet imagine this. Above the Earth, high in orbit, a satellite carries a clock more precise than any watch you've ever worn. On the ground, in a quiet laboratory, another clock ticks away in perfect order. Over days and weeks, the two clocks drift ever so slightly apart. The satellite's clock ticks a little faster than the one on Earth, even though both are built to be identical. The reason isn't a flaw in the machinery. It's woven into the nature of reality itself. Einstein showed us that time is not rigid. It flows differently depending on speed and gravity. Near the surface of the Earth, gravity tugs at time, making it run just a bit slower than it does farther away in orbit. It's such a tiny difference, billionths of a second, that you could live your whole life without feeling it. But the universe is patient, and over great distances or high speeds, these small shifts add up to something profound. Picture time as a river. When you are still, the water flows past at a familiar rate, but change your position, move quickly or climb high above the Earth, and the current shifts. In one place the river slows, each droplet lingering before moving on. In another the current speeds up, carrying moments away more quickly. This is not a trick of perception, it is how the river of time truly behaves. You may wonder if time can flow differently. Which clock is right? The answer is both and neither. Each clock is right for where it is, because time is not a single thread stretched evenly through the cosmos. It is a web of countless threads, each woven through a different path of gravity and motion. Your own body is part of this web, carrying its personal clock, ticking in harmony with your place in space. On quiet mornings, your mind feels the stretch of moments, but your heartbeat still keeps its pace, bound to Earth's rhythm. If you were to leave this surface, to climb a high mountain or drift into orbit, your body's clock would slowly part ways with those who stayed behind. The change would be small, almost invisible, but real enough that scientists must account for it when guiding satellites, spacecraft, and even the GPS on your phone. This means that every journey you take, whether across a room or across the stars, happens inside your own personal flow of time. The difference may be microscopic here on Earth, but it tells us a deep truth. There is no universal clock keeping perfect time for all of us. The universe does not measure moments in the same way everywhere. You can sit with this thought for a while, how each place in the cosmos has its own pace, its own beat. On a distant planet, in the heart of a star, or drifting through interstellar space, the seconds would not match the seconds you know now. And yet, to whoever is there, those moments would feel perfectly normal. They would never sense the difference until comparing their clock to yours. In the stillness of your room, this idea can feel both grounding and expansive. Grounding because it reminds you that your own time is yours alone, the only pace you will ever live in directly. Expansive because it connects you to the clocks of distant worlds, each ticking quietly in its own way, all part of the same vast tapestry. You might think of time as music played across the universe. Here on Earth, the melody is familiar, steady, and comforting. Elsewhere, the tune shifts, faster, slower, higher, lower, yet always in harmony with its surroundings. The beauty of time dilation is that it reveals how flexible this music really is, without ever losing its sense of order. And so, when you feel a morning linger or an afternoon vanish, you can remember that your perception is not the only thing that changes. Beneath your awareness, the deep physics of reality bends the flow of time itself. Your seconds are yours, shaped by where you are, how you move, and the invisible pull of the world beneath your feet. As you close your eyes and listen for the quiet tick of your own heart, you may begin to wonder, if place can shape time so gently, what happens when space itself begins to bend beneath you? What happens when you step onto a curve in the fabric of the cosmos and let it carry you forward? And that is where the next part of our journey begins. The gentle curve of space. You imagine the universe as a soft fabric beneath your feet. Every planet, star, and body makes the fabric sag just a little. This gentle curve is what Einstein called space-time, the stage where time itself bends. And tonight, you will walk along that stage, feeling the tilt beneath your steps. The universe is not empty. It looks like a vast open canvas when you gaze up at the night sky. Yet what appears as space is not nothing at all. It is something invisible, silent, yet real enough to be shaped. Imagine it as a soft, endless fabric stretched in all directions. This is what physicists call space-time, a union of space and time into a single continuous stage where all things exist. In your mind, picture laying a heavy ball on a stretched sheet. The ball presses down, creating a dip in the sheet's surface. Now roll a smaller ball nearby and watch how it curves toward the dip, drawn not by an invisible string, but by the slope itself. This is the universe's quiet trick. Gravity is not a pull from far away, but the bending of the stage beneath you. Every object in the cosmos, from the smallest pebble to the largest galaxy, sits upon this fabric, pressing into it. The greater its mass, the deeper the curve it makes. The sun, massive and bright, makes a wide, gentle hollow in the space-time around it, and the planets, like marbles on that curved surface, follow its slope in endless loops. You are part of this too, standing here on Earth, your body's weight dimpling the cosmic sheet in ways too small to notice, but real all the same. Einstein's insight was that this curvature is not just about space. Time itself is bound to the fabric. So when the sheet bends, time bends with it. A clock resting deep in a curve ticks more slowly than one placed higher up on the slope. And so gravity is not simply a force, but a reshaping of reality, guiding both the paths we take and the pace at which we live. The gentle curve beneath your feet is subtle. You cannot feel the Earth's mass pressing into space-time, but it is there, keeping the moon close, holding oceans in place, and giving you the sense of down. Without this invisible structure, planets would drift away, stars would loosen from their orbits, and time would flow the same everywhere. A strange, cold sameness in a universe without shape. You can sense the beauty in this hidden architecture. Every star you see tonight is shaping its corner of the fabric. Some make small dents, others massive wells that draw in light itself. And between them all, the fabric stretches and flexes, always connected, always in motion. Even now, waves of space-time, born from ancient collisions of stars, may be passing through you, so faint you would never know, yet bending space and time by the width of an atom. Think of walking across a field covered in soft snow. Your footsteps sink, leaving shallow impressions behind. If someone followed in your steps, their path would curve slightly into each print. On the cosmic scale, planets and moons are just footsteps in space-time, not frozen in place, but endlessly shaping and reshaping their trails as they move. And here's the part that feels like poetry. You are not standing on space-time. You are in it. It is not a stage built for you to stand upon, but the very air you breathe, the distances you travel, the seconds you live. When you move through space, you are also moving through time, and both are guided by the same gentle curves. This understanding changes how you see gravity. No longer a mysterious hand tugging from afar, it is instead the quiet slope under your feet. If you could see space-time with your eyes, you might notice the ground under you dipping gently toward Earth's center, the space around the sun flowing in wide arcs, and the very space near massive stars falling steeply into shadowed valleys. And it's not just space that curves. Your path through time does too. If you live deep inside one of these valleys, near a massive planet or star, your seconds would pass more slowly than for someone far above. Time itself leans with the slope, its flow shaped by the rise and fall of the cosmic landscape. In this way, the universe is like a great, breathing terrain, one that holds mountains of time and valleys of space, rivers of starlight and plains of empty darkness. It is not rigid or still, but alive with motion, always adjusting as stars are born, planets move, and galaxies drift like islands in a slow tide. Here in your room, you cannot feel the curvature. But somewhere deep inside you, your body's atoms are obeying its shape, your steps are guided by its tilt, and your life is carried forward along its arcs. You have always been walking across this unseen stage, tracing your own line through its folds. And now, you might begin to wonder, if space-time itself is curved, what happens when that curve touches the flow of time you live in? What does it mean to feel the weight of gravity not just in your muscles, but in your seconds? And so, we follow the slope into the next truth, where gravity's breath begins to slow the clock. Gravity's slow breath on time. You picture time as a river flowing past you. When gravity pulls harder, the river slows and seconds pass differently. High mountains and deep valleys each have their own tempo. And so, even on the same planet, no two clocks truly agree. Time, like a river, seems to flow without pause. It carries you forward, moment by moment, in a current so steady you almost forget it's there. But rivers change. In some places the water runs fast and restless, leaping over stones. In others it slows into wide, quiet bends. Gravity shapes the river of time in much the same way. To feel this, imagine you are standing in a deep valley. The mountains rise above you, their slopes draped in shadow. Here the pull of gravity is slightly stronger. You are closer to the heart of the Earth's mass. If you brought with you a clock so precise it could measure billionths of a second, you would discover something astonishing. It ticks a little slower than an identical clock far up on the mountaintop. This slowing is not a trick of the clock's gears or the observer's eyes. It is written into the nature of time itself. The deeper you are in a gravitational well, the dip in space-time created by mass, the more slowly time flows for you compared to someone higher up. You do not feel it in your bones. You live your life as if everything is perfectly normal. Yet if you and your friend on the mountaintop compared clocks after many years, you would see the difference. Einstein's theory of general relativity revealed this secret a little more than a century ago. Before then, gravity was understood as a force, a kind of invisible rope tugging objects together. Now we know it is the curve of space-time itself, and with that curve comes a surprising side effect. Time bends too. It does not merely tick away in the background, it responds to the shape of the universe. The effect on Earth is small, so small that it takes the most delicate instruments to measure it. But climb higher into the thin air of a Himalayan peak, or the floating quiet of a satellite orbiting far above, and the difference becomes measurable. Seconds stretch ever so slightly as you move away from Earth's gravity. The higher you go, the faster your clock runs compared to one kept down below. And this is not just theory, it is part of everyday technology. GPS satellites orbiting Earth must account for both the faster ticking caused by weaker gravity and the slower ticking caused by their speed through space. Without correcting for these effects, your navigation app would be wrong by kilometers within a day. So every time you find your way home with a glowing dot on a map, you are quietly relying on the truth that gravity changes time. The same principle works in reverse. Near something incredibly massive, like a neutron star or a black hole, gravity becomes so strong that time slows dramatically. Stand near one and your seconds would crawl compared to those of someone far away. For you, only hours might pass, but for them, years could unfold. It is a strange kind of separation, not by distance but by the very rate at which you experience existence. Here on Earth, the effect is gentler, more like a breath than a shove. Gravity leans over your shoulder and whispers to the seconds, telling them to slow down just a little. It does this everywhere, all the time, shaping the hidden rhythm of the world. Even your own body, with its tiny gravitational field, affects time around it in the smallest imaginable way. Every atom you carry leaves a faint signature on the river of time. Think of this when you look at a clock. It may seem like a solid, dependable machine, but in truth, it is in quiet conversation with the universe. Its ticking is shaped not only by springs, circuits, or quartz crystals, but by the depth of the space-time valley in which it rests. Move it higher or lower, deeper or shallower in gravity's field, and its conversation with time changes. This makes our planet a patchwork of slightly different tempos. The clocks in mountaintop observatories do not agree exactly with those at sea level. The satellites circling far above tick differently still. Every one of these differences is real, though too small for human senses. They remind us that time is not a single, universal beat. It is a melody that changes with the landscape. The beauty of this truth is in its humility. You could live a lifetime without noticing it. The difference between the time you experience at sea level and on a hilltop might be less than a fraction of a second in decades. Yet knowing it is there, knowing that time's river flows differently with each shift in gravity, invites a kind of wonder. It means that every place you stand has its own unique rhythm, its own way of measuring your life. Tonight, as you rest, gravity is still here, breathing quietly over your moments. It is cradling your seconds in its pull, letting them pass a touch more slowly than they would if you were high above the clouds. And while you cannot feel this gentle stretch, it is always with you, shaping the tempo of your existence. If gravity can slow the seconds without you ever noticing, what else might shape your journey through time? What happens when, instead of standing still, you begin to move swiftly through the universe's vast stage? And that is where the next chapter will take us, into the dance between speed and the ticking of your clock. Moving through the clock's hands. You drift in a quiet train, feeling the world slide past your window. The faster you go, the more your seconds stretch, even if you can't feel it. Speed itself changes time's rhythm, not just for spaceships, but for you. And tonight, we begin to move faster. The train glides forward with barely a sound. Outside your window, the world flows past in long, unbroken lines. Trees, hills, rooftops drifting backward into the distance. Inside, everything feels still. Your cup of tea rests quietly on the table, steam curling upward in slow spirals. You cannot feel the earth rushing beneath the tracks, nor the subtle rotation of the planet itself. To you, time seems unchanged. But in the deeper language of the universe, your movement is rewriting the rhythm of your seconds. Einstein's theory of special relativity tells us something strange but certain. The faster you move through space, the slower you move through time. It is not an illusion, not a trick of the mind. It is a real, measurable effect, as much a part of nature as gravity. You might picture time as a giant circular clock face, its hands sweeping forward in steady arcs. When you are still, you move straight through the center, letting the hands pass at their familiar pace. When you begin to move, you take a longer path, curving through both space and time, and the hands slow down just for you. Your seconds stretch, even if they still feel normal in your own experience. This is why scientists say motion dilates time. From your perspective, your watch, your heartbeat, and your thoughts tick as they always have. From the perspective of someone standing still, though, your clock and everything about you runs just a bit slower. If you returned from a journey at great speed, you would have aged a little less than those who stayed behind. Here on Earth, with our cars, trains, and planes, the effect is too small to notice. At everyday speeds, time dilation is measured in millionths or billionths of a second. Yet when speeds approach that of light, the effect becomes profound. In the silence of deep space, a traveler racing at near-light velocity could cross the galaxy in what feels like a single lifetime, while centuries pass back home. Imagine two friends. One stays on Earth, the other boards a ship that sails among the stars at tremendous speed. When the traveler returns, the one who stayed has grown older by decades more. For the traveler, the years were gentle and few. This is not a paradox in the sense of something impossible. It is simply the universe's way of keeping the speed of light unbreakable. The truth is, motion and time are bound together like threads in the same cloth. When you pull harder on one, the other must adjust. Move quickly through space, and your path through time must bend to fit the cosmic weave. The faster your journey, the shallower your angle through time, and the longer each second becomes for you. You can sense this principle even without the equations. Think of your life as a walk across a vast meadow. If you stroll slowly, you have time to notice every flower, every shadow. If you run, the meadow blurs, not because it changes, but because your way of moving through it has changed. In a similar way, as you move faster, your experience of time itself changes, even if your senses don't tell you. Satellites circling above Earth already live this reality. Their speed through space makes their onboard clocks tick more slowly compared to those on the ground, while the weaker pull of gravity makes them tick faster. Only by combining both effects, gravity's breadth and motion's stretch, can engineers keep their time aligned with ours. Without this careful balance, the navigation signals guiding ships, planes, and your phone would drift hopelessly out of sync. In this quiet train, you are part of the same dance. Your journey is slow compared to light, but the principle is there. A whisper of stretched seconds, a trace of the universe's precision adjusting to your motion. It is humbling to know that no matter where or how you move, time itself is moving with you, changing just enough to keep the cosmos in balance. And so the clock you carry, in your pocket, in your heartbeat, in your thoughts, is never entirely in agreement with anyone else's. The difference is so slight you could live and die without noticing, but it is always there, written in the fabric of space and time. If speed can bend your seconds, what else can thought alone do? Could ideas themselves be fast enough to change how we see the ticking of the universe? And so we sit down beside Einstein's imagination, ready to see how he dreamed the laws of time into view. Einstein's thought experiments. You sit at a table with Einstein's ideas laid out like puzzle pieces. He imagines mirrors, light beams, and trains to understand time. These gentle, playful images reveal truths that shape the modern world, and you see how thought alone can stretch the edges of reality. You settle into a quiet chair, the room hushed except for the faint ticking of a clock. Before you, there are no complicated machines, no starships, no sprawling laboratories, only a pen, a scrap of paper, and the boundless reach of the mind. It is here, in stillness, that Albert Einstein built his bridges into the nature of time. Einstein's greatest tools were not telescopes or particle accelerators. They were thought experiments, vivid, careful imaginings that could turn the impossible into something almost touchable. He began not with answers, but with questions simple enough to carry in his pocket. What would the world look like if I rode alongside a beam of light? How would a clock appear if I were moving as fast as a train could carry me? Could the laws of nature feel the same, no matter how fast I traveled? The first scene he invites you into is a railway platform in the early 1900s. A train pulls in, its long carriages gliding past at steady speed. On board, a passenger holds a clock made of two mirrors facing each other, with a beam of light bouncing between them. To the passenger, the light travels straight up and down, its rhythm precise and steady. But from your place on the platform, you see something different. Because the train moves forward, the light inside appears to take a diagonal path, up and forward, then down and forward, like a ball bouncing along a moving walkway. This longer, slanted journey means that, from your perspective, the light takes more time to complete its trip between mirrors. The clock on the train runs slower than the one in your hand. And there it is, hidden in a simple image. Speed changes the passage of time. Einstein used this mirror clock image to explain special relativity, the idea that the laws of physics are the same for all observers moving at constant speeds, but that time and space adjust themselves to keep the speed of light unchanged. No matter how fast the train goes, the beam of light never outruns its cosmic speed limit. Instead, time itself bends to make the math and the universe agree. Next, he asks you to picture a flash of lightning striking both ends of a moving train at the same instant. For someone standing on the platform, the strikes are simultaneous, the light from both bolts reaching them at the same time. But for a passenger moving forward inside the train, the front strike's light must travel toward them, while the rear strike's light is chasing from behind. To that passenger, the front flash happens before the rear. Both are correct in their own frames of reference, and so Einstein shows us simultaneity is not universal. He loved these quiet visual games because they made the strange feel natural. They did not demand that you master equations before you could understand. They began with moments you could almost live yourself, trains, mirrors, lightning, and led you into truths that rewrote physics. In another of his imaginings, he places you inside a closed elevator floating in the dark. With no windows, you cannot tell whether the elevator is standing still in deep space or accelerating upwards somewhere in the universe. A ball dropped from your hand falls to the floor either way. From this, he concludes, gravity and acceleration are two faces of the same thing, an insight that would bloom into the general theory of relativity. These thought experiments are gentle in their pace, yet seismic in their effect. They remind us that understanding often begins not with what we can measure, but with what we can imagine. It is in the mental rehearsal of impossible journeys that we first learn their rules. Einstein's mirror clock and train lightning stories are now told in classrooms around the world. Yet they are more than teaching tools. They are invitations. They ask you to step into the scene, to notice what you would see, and to realize that your truth and someone else's can both be correct, even if they seem at odds. And perhaps most beautifully, they show that you can uncover the universe's deepest patterns without ever leaving your chair. The mind is its own spacecraft, able to move at any speed, to any place, so long as it is willing to ask, what if? As you sit with these images, light bouncing in its mirrored cage, lightning splitting the sky over steel tracks, you begin to feel the shape of time not as a rigid line, but as something supple, responsive, alive. It bends and flexes under motion, just as it does under gravity. Which raises the next question: if time can be bent in the mind, what happens when we measure it in the sky? What happens when a real clock leaves Earth's surface and comes back changed? And so we follow those ticking hands into the air to see what airplanes can teach us about the shape of time. Atomic clocks and airplane journeys. You board a plane in the soft light of dawn. In your pocket, an atomic clock ticks its steady beat. By the time you land, your clock's rhythm is just a little different, and the proof of time dilation becomes a quiet fact in your hands. The day begins with a pale, early light spilling across the runway. Engines hum low and steady, and the air holds that particular stillness before a long journey. In your hand is a small, sturdy case. Inside, nestled in layers of padding, is an atomic clock, one of the most precise timekeeping devices humanity has ever made. It does not tick with gears or sweep hands across a dial. Instead, it listens to the whispers of atoms, measuring the exact frequency of their vibrations. Its accuracy is so great that it would take millions of years to drift by a single second. You step onto the plane, your seat by the window catching the first warmth of the rising sun. The clock rests quietly beside you, steady in its invisible rhythm. As the engines surge, you lift from the ground and begin your climb into the sky. The world beneath you falls away, and with it, the weight of Earth's gravity lessens ever so slightly. In that moment, unnoticed by your senses, the clock's tempo changes. It changes because two things are now at play. First, you are moving. The faster you move through space, the slower time flows for you, as Einstein's special relativity teaches. Second, you are higher above the Earth's surface. With less gravity pressing on you, time flows a little faster, as described by general relativity. These two effects work in opposite directions, one slowing your seconds, the other speeding them up. The delicate balance between them can be measured, and it is in that balance that the truth of time dilation quietly reveals itself. In the 1970s, scientists Joseph Haffel and Richard Keating carried out an experiment that captured this in the most human way possible. They took 4 cesium-beam atomic clocks aboard commercial airliners, flying them twice around the world, once eastward, once westward. When the clocks returned to the United States Naval Observatory, they were no longer in perfect agreement with their twins that had stayed on the ground. The differences were tiny, billionths of a second, but they matched exactly what Einstein's theories predicted. Flying east in the direction of Earth's rotation meant moving faster relative to the center of the planet. Special relativity's effect dominated. Time slowed for the airborne clocks. Flying west against the rotation meant moving slower relative to Earth's center, so general relativity's effect from altitude was stronger. Time sped up for the clocks. Both journeys bent time, but in opposite ways. It's easy to think of these changes as negligible, and for our daily lives they are. You will not step off a plane noticeably younger or older than those who stayed home. But the precision of atomic clocks allows us to see what our senses cannot. Time is not absolute. It flows differently depending on how and where you move. Even now, every GPS satellite orbiting above you carries an atomic clock, its ticking constantly adjusted for both speed and altitude effects. If engineers ignored these adjustments, your phone's location could drift by kilometers within a single day. Time dilation is not just a thought experiment anymore. It's part of the infrastructure that guides ships, airplanes, and the footsteps you take on city streets. You glance out the window. The clouds below stretch in soft white fields. Somewhere beneath them, people are waking, clocks are chiming, and moments are passing in rhythms slightly different from yours at this height. It's a reminder that even a short flight is a journey not just through space, but through the fabric of time itself. When you land, the airport feels like any other. Announcements, luggage wheels clicking over tile, the smell of coffee drifting from a nearby cafe. You open the case and check your clock. It is still precise, still faithful to the heartbeat of atoms, but now it is no longer identical to its twin left behind. It has lived through a subtly different version of reality. And as you walk away from the gate, you realize every movement, every climb, every descent changes the way you pass through time, even if only by the smallest fraction. The world is full of clocks and none of them truly agree. If airplanes can shift our seconds in such small but certain ways, what happens to those who live their days far above us, circling the Earth again and again? And so, we look upward to the astronauts who return just a little younger than when they left. Astronauts who return younger. You look up at the International Space Station circling Earth in silence. Its crew lives in a slightly different flow of time than you do. When they come home, they've aged a little less than their friends, and the difference, though tiny, is written in the language of the stars. Far above you, in the deep blue of the daytime sky, there is a place where time moves differently. The International Space Station, ISS, orbits quietly, a silver fragment of engineering gliding at more than 27,000 kilometers per hour. From the ground, it appears to cross the sky in just a few minutes. But for the crew inside, life feels steady. Mornings, meals, and rest following a rhythm that feels familiar. Yet while they work, sleep, and laugh hundreds of kilometers above Earth, their bodies are living through a slightly altered version of time. The reason lies in the same two principles that touch the atomic clocks in airplane journeys: speed and gravity. Up there, astronauts are moving incredibly fast relative to the Earth's surface. According to Einstein's special relativity, that speed causes time for them to slow down compared to someone standing still on the ground. At the same time, they are farther from Earth's center of gravity, where general relativity tells us time flows a little faster. Both effects happen at once, and they compete with each other. In low Earth orbit, speed wins. The ISS crew experiences a net slowing of their time by the tiniest fraction. If you compared their clocks to yours after a 6-month mission, you would find they have lived through milliseconds less than those who stayed on Earth. It's a vanishingly small gap, yet perfectly in line with the mathematics of relativity. You might wonder, how can such a small difference matter? The truth is, it doesn't matter to daily life. No astronaut feels younger when they return. But the fact that it exists at all is one of the most beautiful confirmations of the strange rules that govern the universe. It means that your personal experience of time is tied to the exact path you take through space, and no two paths are ever exactly the same. The astronauts themselves are living examples of the twin paradox, a thought experiment made real. If one twin stayed on Earth while the other spent a lifetime orbiting at high speed, the spacefaring twin would indeed return younger. On the ISS, the effect is small because the speeds, while enormous to us, are still far from the speed of light. But scale up the velocity and the gap would grow into years. Life aboard the station is a balance between the extraordinary and the ordinary. Astronauts float in microgravity, repair experiments, and watch continents pass beneath them in minutes. Yet they also eat meals, chat with family, and mark the passing of days, though day here means something different. The ISS orbits Earth roughly every 90 minutes, giving its crew 16 sunrises and sunsets each day. For them, the visual rhythm of time is unlike anything on the surface, yet their inner clocks, their heartbeats, their breathing, their sleep cycles still follow familiar human patterns, and here lies a quiet truth. Our sense of time is rooted in our bodies, even when the universe's deeper clocks are keeping a different beat. An astronaut can feel the stretch of months away from home, even as physics says they've lived just a bit less than the people waiting for them. When they finally return, stepping out under Earth's heavier gravity, they carry a story written not in words but in the tiniest differences between clocks. Their journey is a reminder that time travel, forward into the future, is not only possible, but happens every day, quietly, above our heads. It is not the kind of time travel in stories with flashing lights and sudden leaps, but a soft, continuous drift, 1 second stretching just slightly longer than it would have otherwise. And so you look up at the sky, knowing that above you there are people moving through time at a pace just a little slower than yours. It's a thought that turns the night sky into more than a blanket of stars. It becomes a map of countless timelines, each moving to its own hidden rhythm. If orbit can slow a person's seconds, what happens when we stand still but change our height on Earth? Can the place you stand, the simple difference between sea level and mountaintop, shape the way your time flows? And that is where we go next, to the mountain and the sea, and the two clocks that never quite agree. The mountain and the sea. You stand on a mountaintop, breathing thin air under a deep sky. Far below, waves break endlessly against the shore. Time passes just a little faster up here than by the sea, and the mountains whisper a truth: height is its own clock. You stand at the edge of a mountain ridge, the morning air cool and thin. The horizon spreads out in every direction, valleys in soft shadow, ridge lines catching the first gold of the sun. Far below, the sea is a restless sheet of silver, its waves folding and unfolding without pause. From this height the ocean looks still, but you know it is never still. And so it is with time. Even when it feels steady, it is always moving, always changing, and here it moves differently than it does below. It begins with gravity's quiet hold. Down at sea level you are closer to the full weight of Earth's mass pressing in from all sides. The pull is just a little stronger, the curve of space-time just a little deeper. Up here, high above the shore, gravity's grip is weaker by the smallest fraction, and according to Einstein's general relativity, where gravity is weaker, time flows a little faster. It is a truth invisible to your senses. Your heartbeat is the same, your watch ticks at its familiar pace, and nothing in the air suggests the world has changed. Yet if you could set two perfectly synchronized atomic clocks, one in a cabin at sea level, the other here beside you, and return months later, they would disagree. The mountain clock would be ahead, its seconds having flowed just slightly quicker. The difference is tiny, billionths of a second over days, perhaps microseconds over years, but it is real. It is a reminder that time is not a universal rhythm, but a local one, bound to place as much as to motion. Height, it turns out, is its own kind of time machine, nudging you forward ever so gently compared to those below. You can imagine the Earth wrapped in invisible layers of different tempos. Each meter upward peels away a little of gravity's hold, letting time slip by just a touch faster. On mountain tops, seconds stretch ever so slightly. In the deep sea, where gravity's pull is marginally stronger, seconds shrink a fraction. We live our lives without noticing, yet our planet is quietly divided into countless overlapping clocks. Scientists have tested this with extraordinary precision. In 2010, researchers used two atomic clocks separated by just 33 centimeters in height and measured a difference in their ticking. It was small enough to feel almost like a magic trick, yet it matched perfectly with Einstein's predictions. Even the height from your head to your feet means that, technically, your head is living through time just a bit faster than your toes. This realization gives the mountain a different kind of beauty. You are not just above the world in space, you are slightly ahead of it in time. Every step upward is a step into a faster rhythm, though your senses never tell you so. It's a kind of quiet freedom, a way of stepping outside the sameness you assumed time to be. As you look down to the shore, you can imagine the waves keeping their own slower pace. The people walking the beach are living through a version of Earth's time that is ever so slightly different from yours. You are separated by more than altitude. You are separated by tempo, two versions of now unfolding in parallel. The beauty of this truth is in its gentleness. It doesn't divide us in any way that matters to daily life. The gap between mountaintop and sea clock is too small to measure without exquisite instruments, yet it is there. A quiet, constant divergence. It says that the way you experience time is shaped by where you stand. Height and motion, gravity and speed, these are the sculptors of time. Each leaves its faint signature on the seconds you live, whether you are aware of it or not. Even now, as the wind moves across the ridge and the sea glitters far below, the difference between you and the shore is quietly accumulating. And so you begin to see a pattern. Time has more than one sculptor. It is shaped not only by place, but by the path you take through space. What would it mean to see these forces working together, weaving a single fabric from two separate threads? And so we turn to the next truth, where speed and gravity meet, and together they shape the very flow of the clock. Time's two sculptors, speed and gravity. You place two hands on the clock of the universe, one shaped by speed, the other by gravity. Together they mold the seconds you live through. Each journey you take is their shared work, unseen yet constant. And you begin to notice their quiet fingerprints on your life. Imagine a sculptor standing before a block of marble. With each strike and curve, the stone changes shape. Now imagine two sculptors, each working from opposite sides, one chiseling with motion, the other with mass. They do not argue. They work together, their tools never clashing, each shaping in ways the other cannot. This is how speed and gravity shape the seconds of your life. You've met them both already, though perhaps you didn't know their names. Gravity's hand is steady and quiet. It bends space and time together, slowing the seconds in its embrace. The closer you are to a strong gravitational pull, a planet's surface, a deep valley, the rim of a black hole, the more it asks time to take smaller steps. Speed's hand is swifter. It stretches seconds not by holding them back, but by carrying you through space so quickly that time must ease its pace to keep the speed of light unbroken. On their own, each effect is remarkable. Together, they form the full rhythm of relativity, the complete way time behaves in our universe. One might slow your seconds while the other quickens them. Sometimes they balance, sometimes one wins. But both are always present, tracing invisible patterns in the flow of your days. Picture again the atomic clocks on GPS satellites. They orbit high above Earth, far from the deep pull of gravity. General relativity says this should make them tick faster than clocks on the ground. And yet they are also moving at thousands of kilometers per hour. Special relativity says this should make them tick slower. The two sculptors work at once, each carving their own influence. The end result, a slightly faster clock in orbit, is the sum of their competing touches. You can see their handiwork in Huffle and Keating's airplane experiments as well. Flying eastward, speed's chisel slowed the seconds more than altitude could quicken them. Flying westward, gravity's hand had the stronger effect, letting time flow just a little faster. In each case, the clock's final time told the story of both sculptors at work. If you could watch your own life from the outside, you'd see the same quiet shaping. Every step you take, every hill you climb, every journey you make through the air, each one shifts your path through time in ways too small to feel, yet precise enough for the universe to notice. From your perspective, your heartbeat and breath never miss their rhythm. But to the cosmic clock, your seconds are elastic, molded by your place and your pace. It's tempting to think of speed and gravity as opposites, but they are more like dance partners. Gravity curves the stage, speed moves you across it. One sets the slope, the other sets the path. Both are needed to understand the choreography of time. Without gravity, there is no curve to slow the seconds near massive bodies. Without speed, there is no stretching of time in motion. With both, the universe becomes a place where now depends on how you move and where you stand. These two sculptors work everywhere, on mountaintops, in orbit, in the silent paths of interplanetary probes. They shape the lives of astronauts, pilots, hikers, and you sitting quietly in your room. Their work is delicate, but its truth is absolute. Every moment you live is a product of their hands. Knowing this changes how you think about time. It stops being an invisible stream carrying everyone equally. Instead, it becomes a landscape shaped by forces you can't see but can describe, measure, and even predict. It means that your time is truly yours, a version of reality sculpted just for you by the exact mix of speed and gravity in your life. You begin to wonder what this means for the seconds you live every day. If even the tiniest changes in motion or altitude shape time, then the very act of existing is a kind of journey through an ever-changing clock. And perhaps most quietly beautiful of all, No two people anywhere in the universe ever share exactly the same time. Light as the ultimate timekeeper. You watch a beam of light cross a dark room. No matter how you move, it always greets you at the same speed. Light itself becomes the ruler by which all seconds are measured, and in its constancy it holds the secrets of time dilation. The room is dim, the air still. You switch on a small lamp and a beam of light cuts through the space. It seems instantaneous, from bulb to wall in less than a blink. You cannot see it travel. You can only see where it begins and where it ends. Yet in that invisible journey lies one of the most remarkable truths in all of physics. Light always moves at the same speed. It doesn't matter if you are walking toward the wall, standing still, or racing away from it. Measure the speed of that beam and it will always give you the same number, roughly 299,792 kilometers per second. It is a rule without exceptions, a cosmic speed limit that nothing can break. And it is this unwavering constancy that shapes the way time and space must behave. Einstein built his theory of special relativity on this very foundation. If the speed of light cannot change, then something else must, and that something is time itself. When you move, the universe adjusts the ticking of your seconds to keep light's speed fixed. Your watch might slow down compared to someone else's, not because it is faulty, but because the laws of nature demand it. Think of light as the ultimate clock, not with hands and numbers, but with pulses. Each wave crest is a tick, each valley a tock. These pulses form the heartbeat of the universe, keeping time for every event everywhere. We may use quartz crystals or vibrating atoms to mark our seconds, but all of them in the end must answer to light's standard. This is why scientists often describe the meter, our basic unit of length, in terms of the distance light travels in a fraction of a second. It is the most faithful ruler we have, unaffected by the quirks of mechanics or the wear of time. No matter where you are in the universe, if you can measure light, you can measure both space and time. The constancy of light also explains the strange effects you've already seen in time dilation. If you're moving quickly, light still reaches you at the same speed, so your seconds must stretch to accommodate that fact. If you are deep in a gravitational well, light still ticks at its perfect rhythm, so your seconds slow to match the bending of space-time. Light is not only the messenger that carries information across the cosmos, it is the referee ensuring that the rules are the same for everyone. Imagine a lighthouse on a dark shore, sending its beam across calm water. No matter how the waves move, the light's path holds steady. You could be rowing toward it or drifting away, but the rhythm of its flashes is unchanged. In this way, light is like the tide of time itself, always advancing, always at the same pace, setting the measure for all things. Every technology we use to keep time, from wristwatches to the atomic clocks aboard satellites, is calibrated against the behavior of light. Lasers, fiber optic cables, and deep space communication all rely on the knowledge that light's speed is constant. If it were to falter even slightly, our maps, our measurements, and our understanding of the universe would crumble. And yet, light does not falter. It is as steady for you as it is for a star a billion light-years away. It is the bridge between moments, the quiet metronome in the background of reality. Knowing this changes the way you see every illuminated room, every sunrise, every star. Each ray is a whisper from the universe's most reliable timekeeper. Every flash and shimmer is part of a clock so vast and precise that it governs not just your days, but the unfolding of galaxies. If light is the standard by which time is kept, then what happens when our own technology must live by its rules? What happens when the tools we carry in our pockets depend on correcting for the bending of time and space just to tell us where we are? And so we look to the sky, to the satellites that circle above, and the quiet adjustments they make every second to keep our maps from drifting into error. The GPS in your pocket. You open a map app and a blinking dot shows exactly where you stand. Above you, satellites race through their own version of time. Without correcting for time dilation, the map would slowly drift away from truth. And so your phone quietly depends on Einstein's equations. You take your phone from your pocket and tap the map. In a moment, a blinking dot appears, pulsing gently over the streets you know. It feels effortless, like magic, as if the world simply knows where you are. But above you, far beyond the blue sky, a network of satellites is working with extraordinary precision, each one tracing its path through space and through time. The Global Positioning System, GPS, is built on a constellation of at least 24 satellites, each carrying an atomic clock. They orbit the Earth at around 20,200 kilometers above the surface, moving at nearly 14,000 kilometers per hour. From that height, they can see vast stretches of the planet at once, broadcasting signals that tell your phone exactly how far away they are. By listening to several satellites at once, your phone can triangulate your position down to meters or even centimeters with advanced systems. But here is the quiet truth. Without relativity, GPS would not work. Every clock on those satellites ticks differently from the clocks here on Earth. Because they are higher above the planet, gravity's pull is weaker, so their clocks tick faster than ours by about 45 microseconds each day. At the same time, they are moving quickly, and special relativity says that motion slows their time by about 7 microseconds per day. The net result? Satellite clocks run about 38 microseconds faster than identical clocks on the ground. That may sound small, but light travels about 300 meters in a single microsecond. If engineers ignored this difference, GPS positions would drift by kilometers within a day, making navigation hopelessly inaccurate. So the system is designed to account for it. The satellite's clocks are pre-adjusted before launch, set to tick slightly slower on Earth so that once they are in orbit, they keep perfect time from our perspective. Ground stations continually monitor them, correcting for the tiny changes caused by orbital shifts, temperature variations, and even the bending of space-time around the Earth. When you see that blinking dot on your phone, you are looking at the product of Einstein's theories, quietly at work in your pocket. Every turn you make in a city, every path you trace on a mountain, every ship guided into harbor, all of it depends on this careful synchronization of time across space. Your phone, though it seems like a simple tool, is part of a planetary conversation between the ground and the sky. It is remarkable to think that your morning walk is mapped using principles born in thought experiments about trains, beams of light, and moving clocks. What began as questions in Einstein's mind now keeps millions of lives moving safely and efficiently every day. You might never feel the satellites above you, their speed and altitude pulling at their seconds. But each time you find your way with GPS, you are participating in a constant, invisible proof of relativity. It is the same truth that bends time for astronauts, for mountaintops, for moving trains, now woven into the rhythms of your everyday life. And yet, this is only the gentlest expression of time dilation. Far from Earth, in the deep and dangerous wells of space-time, the stretching of seconds becomes far more dramatic. So much so that light itself can seem to pause. And so we turn our gaze to the darkest places in the universe, where gravity's hand is strongest and time's flow slows almost to a standstill. Black holes and stretched seconds. You peer toward a black hole's edge where light itself lingers. Here, time slows so much that a second could last a lifetime. From far away, you would see an object freeze in place, and the boundary between now and forever blurs into shadow. Far out in the silent dark, there is a place where time surrenders, a place where gravity's pull is so fierce, so absolute, that even light, the universe's ultimate timekeeper, cannot escape. This is a black hole, and it is here that the stretching of seconds reaches its most extreme form. You begin your approach slowly, drifting through the emptiness of interstellar space. Far ahead, the black hole is invisible against the darkness, yet you know it's there from the way nearby stars' light bends and swirls, as though sliding along the rim of a vast whirlpool. Surrounding it is the event horizon. the point of no return. Cross it and no signal, no particle, no whisper of information can make its way back. From a safe distance, your ship's clock ticks normally. Your seconds feel the same as they always have. But as you draw nearer, gravity's pull grows, and the river of time begins to slow. At first it is only a tiny shift, something no sense can detect. Yet with each kilometer closer, the difference becomes more profound. For you, inside the ship, life continues at its usual rhythm. Your heart beats steady, your thoughts moving naturally from one to the next. But for an observer far away, watching through a telescope, something strange begins to happen. Your approach seems to slow. Your ship's signals arrive farther apart in time, and as you near the event horizon, your image freezes, suspended at the edge, fading into a dim red glow. To them, you never cross. From their perspective, you become a permanent fixture at the black hole's border. This is gravitational time dilation pushed to its absolute limit. The curvature of space-time here is so steep that time for you, close to the event horizon, is stretched almost infinitely compared to the outside universe. A minute by your reckoning could correspond to centuries, millennia, even the full lifetime of civilizations far away. If you could send a message from this brink, it might be received by descendants of those who first launched you, long after your home planet had changed beyond recognition. From your perspective, though, only a short conversation has passed. The black hole's ability to slow time comes from its mass being packed into an unimaginably small space. A star, many times the sun's mass collapses under its own gravity, compressing matter until space-time curves inward on itself. Here, gravity does not merely tug, it reshapes the very stage on which the universe unfolds. In the center lies the singularity, a point where density and curvature become infinite, and our current understanding of physics can no longer describe what happens. Between you and that center, time's meaning dissolves. If you were to fall inside, you would carry your own ticking clock, still feeling each moment as normal. But the rest of the universe would race ahead without you, its future rushing past in the blink of your slowed seconds. From afar, this extreme slowing is part of the black hole's mystery. It makes the edge, the event horizon, a kind of one-way boundary not just in space, but in time itself. It is the ultimate demonstration that time is not a constant backdrop. It is malleable, flexible, and vulnerable to the forces of gravity and speed. Standing on this precipice in your mind, you see how all the gentle versions of time dilation you've encountered before, on mountaintops, in airplanes, in orbit, are faint echoes of what happens here. The same rules apply, but magnified until they become almost incomprehensible. It leaves you with a lingering thought. If time can stretch so dramatically in the presence of great mass, what happens when we imagine two lives that take very different journeys through it? And so we step into a famous thought experiment to see how two twins can live side by side in one moment and yet be separated by years when they meet again. The twin paradox. You meet two twins who take very different journeys. One stays on Earth, the other travels near the speed of light. When they reunite, they've lived through different amounts of time, and the bond of family becomes a mirror for the bond between time and motion. You imagine two twins born moments apart. They share the same first breath, the same first sunrise, the same early rhythm of life. For years they grow together, their clocks ticking in perfect unison. Every birthday, every shared meal, every night of stargazing, they live in step, as if time itself has agreed to keep them matched. But then one twin decides to travel, not to another city or across the sea, but into the vast dark of space, aboard a ship that will reach speeds unimaginably close to the speed of light. The other twin stays on Earth, watching from the ground as the craft shrinks to a point and vanishes into the quiet sky. From the traveler's perspective, the journey is long but not unbearable. Perhaps a few years pass. The ship glides through starlight, its engines a low and constant hum. The traveler's heart still beats in the same rhythm, thoughts still flow at the same pace. Inside the cabin, nothing feels strange. Seconds arrive just as they always have. But back on Earth, the other twin lives through a different story. Decades pass, seasons turn, friends and neighbors grow older, technologies change, cities rise and fall, and the world moves steadily forward. To the earthbound twin, the journey is not a handful of years, it is a lifetime. When the ship returns and the twins stand face to face again, the difference is undeniable. One twin's hair is silvered with age, the other's face still carries the youth they both once shared. For the traveler, only a short time has passed. For the one who stayed, many years have unfolded. This is the twin paradox, one of relativity's most famous thought experiments. It's not truly a paradox in the sense of a contradiction. Rather, it's a reflection of how time dilation works when two people take different paths through space-time. The traveling twins' high speed through space means their path through time is stretched. They move closer to light's ultimate speed limit, and so their seconds lengthen compared to those of the twin on Earth. Special relativity explains it cleanly. The laws of physics hold for both twins in their own frames of reference, but the symmetry breaks when one accelerates away and then slows to return. That acceleration changes the geometry of their journey through space-time. It's not the departure or the arrival alone that causes the age gap. It's the entire path taken. In truth, this scenario is not just an idea. We've seen its seeds in experiments, atomic clocks flown in jets, astronauts orbiting in the International Space Station, particles in accelerators living far longer than they would at rest. The universe has confirmed again and again that motion can stretch time. What makes the twin paradox so compelling is not just the physics, but the human image it creates. Two people bound by family step into different streams of time and reunite to find that those streams have not flowed equally. It's a reminder that time is not a single river carrying us all forward together. It is a network of countless currents, each shaped by the journeys we take. Standing between the twins in your mind, you might feel an ache for the years lost to one and the youth preserved in the other. But there's beauty too, in knowing that time is not only something we measure, but something we can travel through in different ways. If speed alone can create such a separation, imagine what happens when we combine it with the most extreme gravitational fields in the universe. Could entire civilizations live and die while for you only a year has passed? And so we turn our gaze outward to the stars, to see how time's flow changes when worlds orbit close to blazing suns or skirt the edges of cosmic giants. Time dilation in the stars. You imagine living on a distant world orbiting close to its sun. There, a year could pass for you while centuries flow by elsewhere. The cosmos becomes a patchwork of different clocks, and your place in it feels both small and deeply connected. Far from Earth, beyond the reach of our familiar constellations, lies a star you have never seen before. It burns white gold in the darkness, steady and bright, wrapped in the invisible curve of its own gravity. Around it, planets trace their orbits, each carrying its own flow of time. If you could step onto one of those worlds, close to the warmth deep inside the star's gravitational well, your life would unfold at a different pace than life anywhere else in the universe. Here, gravity's sculpting hand is strong. Seconds pass more slowly in its embrace, drawn out by the depth of space-time's curve. A single year on this planet might match decades, even centuries, for someone far away in the galaxy. You could live a lifetime here, look up at the same familiar sky, and know that elsewhere, whole civilizations might rise and fall before your hair turns gray. The difference is not something you would feel. Your own heartbeat, your own breathing would keep their familiar rhythm. Your friends, your family, your community, all would share the same local flow of time. It would be only when you compared your clock to a distant one, perhaps a signal from a spacecraft orbiting far from the star's pull, that the truth would emerge. This is not science fiction. It is simply the geometry of the universe. The deeper you are in a gravitational well, The slower time moves compared to the outside. And stars, especially the massive ones, carve wells far deeper than anything on Earth. Now imagine a binary system where two stars orbit each other. One small and cool, with planets far from its surface. The other massive and hot, with worlds skimming close to its searing light. On the distant worlds, time flows quickly. On the close ones, it drifts slowly. From one system to the other, now is never quite the same. The cosmos is full of such mismatches. Around neutron stars, incredibly dense remnants of exploded giants, time slows more than you can easily imagine. A person living near one could watch the wider galaxy age and change at a dizzying pace while their own years crawl forward. Near a black hole at the center of a galaxy, the effect becomes so intense that a single orbit might encompass eons for those outside. It is in these places that you begin to see the universe as a patchwork quilt of clocks. Each star, each planet, each moon keeps its own time, measured by the balance of speed and gravity in its skies, and each is valid in its own frame of reference. There is no single universal beat to which all must march. This idea makes the night sky feel different. When you look up from Earth, the stars seem frozen, their light arriving together in one grand still picture. But behind that picture, each one is moving through its own stretch of seconds. Some are aging more slowly than we are, others more quickly. The light you see tonight may have left its star in what, for that star, feels like a different era entirely. It also changes how you think about journeys. To travel to such a place is not only to cross space, but to cross into a new rhythm of time. You could leave Earth and return to find the planet older than you expected, the voices you remember faded into history, the world's map rewritten. And yet, in this patchwork, there is connection. Every clock, no matter its pace, is part of the same fabric. Every second, whether stretched or quickened, is woven into the same universe. It's as if the cosmos is playing a symphony, each instrument with its own tempo, yet all part of one piece. If the stars can shape time so profoundly, what happens to a traveler who leaves one tempo and returns to another? What would it mean to drift for years in the quiet of deep space, only to come home and find the world moved on without you? And so we follow such a traveler, carried through long years of silence, toward the strange reunion that awaits on the long journey home. The long journey home. You drift in the quiet of space, watching galaxies pass like lanterns. The seconds on your ship stretch, while faraway years speed by. When you finally return, your home has aged more than you, and you carry the strange gift of extra time in your bones. The ship hums softly around you, a steady heartbeat in the vast silence. Outside, space is a black ocean scattered with islands of light, galaxies drifting slowly past like lanterns on a night tide. You have been traveling for years by your own reckoning, though you know the clocks on distant worlds have counted much more. Here, in the deep corridor of your journey, time is both faithful and strange. Your vessel moves at a fraction of light's speed, swift enough that the familiar rules of time have begun to bend. Inside, each second feels ordinary. You sleep, you wake, you mark the days in quiet rituals. But beyond your small cabin, the universe has been racing ahead. The balance between your speed and the pull of gravity along your path has stretched your seconds, slowing your passage through time compared to the worlds you left behind. You think of home often. When you departed, the streets were lined with trees just beginning to turn green. You can still picture the faces of those who waved from the edge of the launch platform, their voices lost in the hum of engines. You wonder how many seasons have passed for them. For you, perhaps a decade. For them, perhaps 2, perhaps 3. Messages reach you from home, though never in perfect step. By the time you read them, the senders have already lived months or years beyond the moment they pressed send. Your replies travel back at the same patient pace, arriving in what, to you, feels like the near future, but to them is a faint echo from the past. You live in a constant exchange with ghosts of earlier moments. The stars nearest your course grow brighter, then fade as you pass them. Sometimes you turn off the ship's lights and simply watch, letting the shapes of galaxies fill the windows. You imagine each one as a vast clock face, its arms turning slowly in spirals of starlight. In each, time flows at its own rhythm, slower near massive hearts, faster in the open dark. Yet all of them move forward, each keeping its own truth. At last the day comes when the blue-white curve of your home planet appears ahead. It turns slowly beneath a thin veil of clouds, looking much the same as it did when you left. But you know that the sameness is an illusion. On the surface, generations may have shifted, buildings may have risen where empty fields once lay, songs and voices you remember may have been replaced by others. The descent through the atmosphere feels like falling back into an old dream. The air is heavier here, the sounds sharper. You step onto solid ground, feeling gravity's pull welcome you home, yet you carry a secret, a treasure of time itself. Your body is younger than it would have been had you stayed. The years you did not live have been spent elsewhere, in the swift currents of the wider universe. Reunions are both joyful and strange. Some faces you know, others belong to people you've never met, but who know your name from stories. You find yourself straddling two timelines, one lived by your own clock, the other by the world's. You are both from here and from another era entirely. As you walk familiar streets, you feel the quiet truth settle in you. Every long journey changes more than just where you are. It changes the shape of your life, stretching and folding your moments in ways that only the universe's deepest laws can explain. And as the days pass, you begin to wonder, if time can be bent so far on grand journeys, what does it mean for the way you live your life right here, right now? Can the awareness of time's flexibility change the way you move through ordinary days? And so we return to the ground, to the heart, and to the daily rhythm to see how living with time's flexibility can shape the life you choose. Living with time's flexibility. You return to your own room, your own breathing, your own small clock. The vastness of time dilation folds into your daily life. You see the seconds not as fixed, but as gentle, shifting companions. And you rest knowing you are always part of their quiet dance. You are home again. The walls are familiar, the air still carries the scent of the seasons you remember. Outside your window, light falls the same way it always has, slow, warm, and without urgency. And yet you cannot look at time in the same way you once did. You have seen it bend in the hands of gravity and stretch in the company of speed. You have watched it drift apart for astronauts and satellites, for mountaintops and seashores, for worlds that circle close to their suns, and for ships that cross the darkness between stars. You have learned that it is not the rigid metronome you once imagined, but a soft, pliable thread that shapes itself to each journey. Now, in the quiet rhythm of daily life, that understanding becomes something more personal. The seconds you live are not just measurements on a clock, they are companions. They walk with you at a pace shaped by where you stand, how you move, and the unseen curves of space-time beneath your feet. When you stroll through your neighborhood, you are moving in a different time than someone sitting in a chair across town. When you take the elevator to the top of a tall building, your seconds lengthen just slightly compared to those waiting in the lobby below. When you board a train, a bus, or even ride your bicycle, you are stepping into a subtly altered flow of time, unique to your path. These changes are too small to touch your senses, but knowing they exist changes how you feel them. You realize that every person you pass on the street is living in their own tempo, not by choice, but by the natural design of the universe. We are all in sync enough to share moments together, but never perfectly aligned. There is a kind of quiet poetry in that. It also means that no two lives are ever truly the same, even if they begin together. Your version of the past, present, and future is shaped not only by memory and hope, but by the invisible hands of speed and gravity sculpting your seconds. You have been living a private version of time all along, and so has everyone else. There is comfort in this thought. It makes the present feel more intimate, more yours. You do not own time in the way one owns an object, but you are its sole witness from your point in the universe. The seconds you live will never belong to anyone else. Knowing time's flexibility can also change how you treat it. You stop thinking of it as something that slips away, irretrievable and lost. Instead, you see it as a companion that travels with you, adapting to your journey. It is not a fixed resource to be spent. It is a relationship to be lived. On some days, you may feel like you are racing forward, deadlines rushing in, hours collapsing into each other. On others, you may feel time stretch out before you, calm and generous. Both are true and both are part of the same dance. When you lie in bed at night, listening to your heartbeat, you can remember that this pulse is also a clock. One tuned to your own gravity, your own speed, your own place in the world. It is a reminder that you are part of the fabric of space-time, not apart from it. Every breath you take is a negotiation with the universe's rules, a quiet agreement on how fast the moments will flow. And as you rest, you might feel a deeper peace, because you know now that time is not an indifferent force rushing past you. It is a gentle companion, shaped by your path, and shaping you in return. If your life is always lived in your own personal time, then returning to the ordinary is not really a return at all. It is simply another journey, one that begins and ends in the same place, but is made different by the awareness you carry. And with that awareness, you can't help but wonder. If you could share this way of seeing with others, if you could tell the story of time not as a rigid march, but as a flexible dance, how would it change the way they live their own seconds? And so we arrive at the final chapter, where the vast science of time becomes a quiet reflection, a closing breath, and a gentle step back into the flow of the universe.